Sir, good morning, sir.
Good morning, Sai.
Sir, in the week 11 assignment, I have one doubt, sir.
Okay, just give me a second. Let me. Okay, so yeah, tell me. Yes, Sai, go ahead. Sai, you can go ahead. Can you understand? Can you hear me?
Sir, yes, sir, we can hear you.
Hello?
Yes, Sai. Sai, can you hear me?
Yes. Yes, sir.
Can you said you have a assignment doubt in assignment
11,
number
sir.
11. Yeah.
Yes, sir.
Can you refer to the question? Specific question?
Question number 6, sir.
Question number 6. Okay.
Uh,
Okay.
at U1 equal to 0, if surface tension is not 0, then options are phase speed is.
I've shared my screen. Is this correct? You are referring to this one, right?
Question number 7, sir. 7.
7. Okay. Consider the same configuration as described in question number 5. So you have basically two fluids, different velocities U1, U2, rho 1, rho 2. Okay. Now we said U1 equal to U2 is 0, which means that there is no flow.
Yes.
Then rho 1 is greater than rho 2. The fluid above is denser than fluid below. And surface tension is 0. Okay, meaning at the interface there is no surface tension. Which of the below statement is the correct choice? Yes.
Sir,
Tell
but
me.
in the given assignment, the surface tension is not 0.
Yeah.
Okay.
In the given assignments, I didn't understand the question.
That means in the assignment given to us, once I check the website, sir. 1 minute, sir. If I check the website. In the website, I think it is surface tension is non-zero.
No. That cannot be. Can you show me on the screen and then share it and show it on the screen? What do you see?
Minute. I think it's my mistake. I think it's my mistake. Okay. It's my mixture, sir. It is E0 only. Okay.
It is 0 only, right?
Yes, sir. It is 0
So
only.
you have any doubts on the question?
No, sir. I understand.
Okay, okay. So
Eighth
you
question, sir.
basically, okay.
Sir, in eighth question,
Eighth question is at the bottom of the screen. Yes.
in Elmos instability, the uniform density primary driving causes the instability. That means
What is the primary driving cause of the instability? What is the main mechanism for the instability? What do you think is the main what is the main force which is causing the instability?
generally gravitational forces are main for instability.
No,
If there is
I'm not going to
density
give I'm not going to give you the answer. You have to think and ask yourself what is the correct force. Okay.
gravitational
This has
forces,
been discussed in the course.
yes,
Sorry, say that again.
sir. I think gravitational forces will drive the instability. No, sir. There is a density difference between the fluids. Okay, uniform density.
Yes, but you read the question carefully. You read the question carefully because I can't. What you're asking me. I mean, I can't be answering the question for you. Okay.
I think that there is a non-uniform density. That's why I think that the answer is gravitational. Sir.
Yeah, but
Okay.
you have to ask yourself if otherwise, it's
Now
uniform
I
density has
understand.
been given, Kelvin and moles is given. So you ask yourself what is the mechanism for instability?
Okay.
Okay. Huh?
Okay, sir. Then I am done with the questions, sir. Today.
Yeah, yeah. Okay. So are you basically have you completed week number 11?
Yes, sir.
Okay. So any doubts on any of this?
No, sir. I understand the concept of week number 11.
Okay. So again, where are you studying again? Sorry, I forgot.
At NIT Durgapur, sir.
NIT Durgapur. And you are studying what?
MTech final year, sir. Second year.
MTech. Okay. MTech second year. Very good.
Sir, is
What are you planning to
PhD
do next?
available? PhD, sir. I am trying to do PhD.
Okay. You can apply to various places.
Yes, sir. Currently I am if I got admission in IIT Bombay or IIT Hyderabad, I am trying for 4 institutes, sir. IIT Bombay, IIT Madras, IIT Bangalore, and IIT Hyderabad. For these 4 institutes, I
Okay,
am
good.
trying to get up.
Okay. Okay. All are good places.
Yes, sir. Sir, is there any requirement for PhD in IIT Hyderabad, sir? At present?
It wouldn't be right for me to tell right now. Let's keep it to the discussion on this. But you can feel free to drop me an email and I will tell you whatever I can. Huh? Okay.
Okay, sir.
I'll be happy to tell you whatever I know, but it's better to take it up after this discussion. Huh?
Okay, sir.
I'd like to keep the discussion largely to this. I'm happy to you basically reached all the way to week 11 and another week to go in the course. Okay.
Okay.
And in the next week, there are some advanced topics of active research. In sort of open questions as well are addressed. Okay, in the next week number 12. There is some of it is active areas of research. So obviously the lectures are not very extensive, meaning it's not possible to cover a large give an overview of all the possible research that's happening. But I've discussed a few problems on contact line hysteresis. Then we've done in week number I believe week number 7. We did the uniform thin film downward incline.
Yes, sir.
Thin film downward incline plane. So essentially, I revisit that problem, but instead of being the uniform film, we will now have a contact line.
Okay.
So essentially,
That
that complicates matters quite a bit. Huh?
That means inclined in a curved surface, inclined down in a curved surface.
No, not down a curved surface. It's an incline, but let me just see if I can share what I'm saying. I'll share my screen. And I basically just logged in from my iPad. Can you see my iPad screen?
Yes, sir.
Okay, just let me open that. So essentially, you can have a uniform film. This is an inclined plane, and you can take a uniform film of, let's say, that is moving down the inclined plane. Correct?
Yes, sir.
This kind of a problem has been studied, and you can ask what is the velocity profile inside this. It will be like a fully developed flow with a half parabola. These kinds of problems have been done, but it's very common to also encounter problems where you have a plate, but then the thin film is actually has an end, meaning it's a thin film, but it has a boundary. Okay, so this could be liquid, and this is air, and this is a solid. So here you have, we've had a discussion on contact lines, correct?
Yes, sir.
Contact angles where you say that, oh, this angle is theta. And you can ask a variety of questions. What is the shape of a puddle? What is the shape of this interface, and so on? But all of those questions are static questions, meaning when the liquid is not flowing. But if the liquid is flowing, after some time, this liquid will basically be at a different location. It will basically flow like this and come down here, and then eventually come down like this. So one of the questions is, what happens to this angle? Is this angle, is this theta? Is theta same as theta y, the Young's angle? The answer is no, it is not. Okay. So this is what is referred to as a dynamic contact angle, an angle which is different from the static angle. Okay. And the most interesting thing to think about is, if this was a material point, you know what a material point is?
Material quantity.
Material point. For example, you take a point of the fluid, which is just below the interface. Okay.
Okay.
But it is at the interface. Basically, it's a point on the interface. It belongs to the fluid. Okay.
Okay.
Correct?
Okay.
It belongs to the liquid. Now, what would happen if this fellow is going down? Then this point would come down like this. It would come down, and eventually, this point will have to turn. Correct?
Yes, sir.
You see the zoom, but it cannot turn because as soon as it comes on the surface, it has to obey no slip condition.
Yes, sir.
If it obeys no slip condition, the plate is stationary, right? The solid is not moving anywhere. So this point
sir.
cannot go anywhere.
Okay.
But what you see in experiments, what you see in real life observation is that point has actually been moving. The point is actually moving.
Okay.
So if you actually do the analysis with no slip condition at the contact line, then what you will get is a singularity. The shear stress will go to infinity at the contact line.
Okay.
This is a very interesting problem in classical fluid mechanics. I mean, we are applying classical boundary conditions, all well-known boundary conditions, solving it with the same continuum fluid mechanics, and you get a singularity. So understanding what is the cause of the singularity, understanding how to fix the singularity is a huge area of research. And there have been several theories, and in my own lab, research lab, we work on problems like this. That's one of the problems that we work on. Okay. So you'll see this, these are advanced topics, of course, but there's a discussion of some of these points in the in week number 12.
Okay, sir.
Okay. So this all of this falls under the discussion of moving contact lines. Okay.
Okay. Sir, what is the definition of vertex sheet, sir? Sir, your voice is not audible, sir.
What's the definition of vortex sheet? Let me just show you.
What is means?
So a sheet, vortex sheet is the Kelvin-Helmholtz instability. If you notice, you have an interface and you have a fluid of different speeds, right?
Yes.
So at the interface, at this location, right at the interface, you have del u by del y is non-zero. Only at that location. Del u by del y is 0 for y greater than 0. Let's say the interface is at y equal to 0. Okay. And del u by del y is equal to 0 for y less than 0. Correct?
Yes, sir.
So basically now essentially del u by del y equal to not equal to 0 at y equal to 0. Okay.
Okay.
So the way you should think about it is your velocity is a step function. U of y is a step function.
Yes, sir.
Correct?
Yes, sir.
Del u by del y will be a delta function. You know what a delta function is?
They're increasing or decreasing linearly.
No. A delta function is a function which basically has um, so a delta function is a special kind of function where if you say um, um, f of a is minus infinity to infinity. F of y into delta of y minus a dy. Okay. The idea is that this is the formal definition of a delta function. What it basically does is if you look at this delta function, a delta function is defined like this. Delta of let's say y. Delta of y is defined like this. It is 0 for y. It is 0 for y greater than 0. It is 0 for y less than 0. Okay.
Okay. Yes, sir.
Correct? But
Yes.
apart from that, but integral of minus infinity to infinity, delta of y is equal to 1. This is the traditional definition. Okay, which means that you have a function which has basically very in simple sketch, you have a function which is 0 everywhere. It is 0 everywhere, but except at that location, it has a very large value at this point. Okay.
Okay.
So if you integrate this function, you don't even have to integrate it from minus infinity to infinity. You can integrate it from any small value. Let's say minus epsilon to plus epsilon. Delta of y will still be equal to 1 because epsilon could be here. Okay. So what this function tends to do is this is referred to as a delta function. Delta function essentially what it does is it tells you that the function has only a value at one location, non-zero value. At everywhere else it is 0. So if you think about it, del u by del y is a delta function because del u by del y is 0 above, del u by del y is 0 below, and only at the interface it has a non-zero value. Correct?
Yes, sir.
There are ways to think about the delta function, other ways to think about it. So if you take a velocity profile like this, here's your interface. If you think of a velocity profile, like this, okay.
Okay.
So you see that the velocity is rapidly decreasing from this point here, let's say point 1 to point 2, correct?
Yes, sir.
So let's call this thickness of the interface. Let's call this a thickness of the interface. Let's call that, let's give it some variable. Let's give it some name. Let's call this as delta, capital delta. So as delta goes to 0, what ends up happening is that this interface becomes steeper and steeper, correct?
Yes, sir.
And eventually it approaches a step, correct?
Yes, sir.
Sharply varying profile approaches a step profile, right?
Yes, sir.
Now, if I go back to the sharply varying profile, in the sharply varying profile, del u by del y is not equal to 0 over a region of delta, correct?
Yes, sir.
Over this entire region of delta, it is by and large non-zero, correct?
Yes, sir.
But it has a very high value. Now we can make a plot of how does del u by del y look like. Del u by del y would look like this. Del u by del y, it is by and large 0 away, but then very close to delta. Once you approach delta, it basically has a very large value. Okay, and then again from the bottom also it's exactly the same. It's 0. This is the value, this is the profile of del u by del y. Okay, rather I should say this. This is the profile of del u by del y versus y, correct?
Right. Yes, sir.
Everywhere else it is 0, only in the middle it is non-zero. Now why am I talking about del u by del y? Because if I see z component of vorticity, z component of vorticity would be del v by del x minus del u by del y. In this case, this is 0. So it is simply minus del u by del y. Correct?
Okay. Yes, sir.
So what do you learn from this? What you learn is that vorticity, I'm highlighting this region here in yellow. Vorticity is really there only in this region. In this narrow region, vorticity is there. Everywhere else, vorticity is 0.
0.
Correct? This is a
Yes,
region
sir.
of intense. This is a region of intense amount of vorticity, right at that location. If you now make this into a step profile, then what happens to the vorticity? If you make it into a step profile, the vorticity will be 0 everywhere. It will be 0 here, and it will have a very large value only in the center. Meaning all the vorticity is concentrated only in the center along the interface.
Okay.
Such a idealization is called a vortex sheet.
Okay.
So in the problem that was discussed in the course, you have a step like this. So this is a vortex sheet.
Okay.
Okay. The interface actually becomes a vortex sheet because all the vorticity is confined only to that region, nowhere else. Okay.
Okay. Yes, sir.
So if there are no more questions, can we stop the recording?
Yes, sir.
Any more questions, Sai?
No, sir. No, sir.
Okay, Sai, thanks for the interest. Huh? I'll see you again next week.
Okay. Thank you, sir.